My project deals with the challenge of balancing temporal and spectral resolution in signal analysis. The shortcoming of traditional methods like STFT and an algorithm I kind of developed from the inspiration of algorithms like CQT and other multi-resolution techniques. This GitHub repository I've uploaded. These two are the sounds that I have used. I had to convert this into .wave, and these two notebooks. The code is in there, and the code is similar. Just the it I ran it on two different sound. I don't want it to make it cumbersome, so I separated it, and that's the README file. So, in signal processing, we often analyze signals both in uh, uh, time and frequency. High time resolution means that you know exactly when a change happens at a given time, and high spectral resolution means you know exactly what frequencies are present. But there is this trade-off to achieve high spectral resolution, uh, basically very small delta f, so you can distinguish closely spaced frequency. You need a longer window, which lowers your temporal resolution. And if you want high temporal resolution, you need a shorter window, which reduces your frequency precision. Both are crucial. For example, when analyzing music, speech, or ECG, you care about uh, both when something happens and what frequency content is involved. We have been using STFT for a very long time because of the um, assumption that the frequency at a point depends on the nearby signals, not on will depend more on the nearby signals than the signals at the end. So STFT came into the picture, but there are some limitations of STFT. It uses a fixed window size for all frequencies. But we know that low frequencies need longer windows, high frequencies need shorter windows. So STFT fails to adapt, and poor representations when the signal contains both low and high frequencies. So other techniques like wavelet transform and CQT were developed. In CQT, frequency bins are spaced logarithmically, um, and each bin has the same Q factor. Q factor is basically center frequency divided by the bandwidth. And to maintain constant Q, lower frequencies use longer windows, and higher frequencies use shorter windows. And inspired by this variable window idea, I developed a very simple algorithm. Instead of logarithmic scale, I have just used a simple uh, linear scale, which uses three different fixed window sizes. Um, and I computed spectra for each window. Then for each frequency band, I selected peaks from the spectrum computed at the appropriate window size. So lower frequencies were picked from the longer window spectrum, and higher frequencies were picked from the shorter window spectrum. So in this way, ensuring that both higher and lower frequencies are coming from a very stable and a proper window size. So this approach is similar and easier to implement than CQT, yet captures the idea of multi-resolution. Now I'll walk you through the code. So So after uploading the sound, original sound, I'll play the sound once. I have used the constant Q transform simply from the library, and this is the spectrum that I got. This show that the so from the spectrum it can be seen that the horizontal line thickens at low frequency, these low frequencies, so which basically reflects a poor time resolution, but good frequency resolution, and the horizontal line at the higher frequencies um, reflects better time resolution but poor frequency resolution. So the audio that we got from after applying CQT is like this. So now I'll be talking about the approach that I have used, and I have named it as improved STFT because it uses um, like the same window technique, just the variable window sizes and the linear time scale, unlike in CQT, which uses logarithmic time scale. So these are simple peak detection. Basically, after above a certain threshold, we'll consider those peak, and below that threshold, we'll ignore those peaks. Then this DFT analysis is basically the computing DFT on using the window W. This will run 3 times for all the for all the window sizes. I have considered 3 window sizes, and it will run 3 times and will return the magnitude and the phase, and the peak interpolation, which will be applied after this DFT analysis and peak detection. So this function basically returns arrays of interpolated frequency bins, magnitude, and phases. So basically, what peak interpolation is, it is a technique which is used to estimate the true frequency and magnitude of a spectral peak more accurately than by just by simply taking the discrete bin from the FFT results. So when we calculate our DFT or FFT of a signal, the frequency resolution is limited by the FFT size that we pick. Uh, Peaks may not fall exactly on a frequency bin, but could be somewhere between these frequency bins. So if we just pick the maximum bin, we miss precisions. So peak interpolation refines the peak location, magnitude, and phase by fitting a curve to the neighborhood of the peak. And here I have fit the parabola using parabola for the curve using these 3 points, these three nearby points. So here is the main code for my approach. But before that, I'll go through this. These window size. Um, so I have chosen this Hamming window, and the window shape is same for all the um, windows, but the sizes are different. And for low frequency, I'm taking a longer window size, and for high frequency, shorter window. And the band edges, basically it will be used in the main code, which basically decides which frequency which frequency we are supposed um, for a particular frequency we are supposed to use which particular window. These these FFT sizes for three different bands. We have taken T is equals to -20. This is in decibel. Will like in the code above, to I've converted this decibel into uh, we have changed it here from decibel into amplitude ratio. So now back to our main code. Um, I have initialized the window sizes here, and this is of no use. And the window will slide over the signal which has been extracted from here. Then applied the DFT analysis for all the three window sizes simultaneously. It will run independently. Uh, then the peak detection will happen for all the three, and followed by peak interpolation. So um, and finally, for each frequency that we have collected from here, from all the three windows, we we uh, 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 we select peaks from the corresponding windows interpolated peaks. Basically, band edges I have defined here. Somewhere it was. Yeah. So band edges I have defined here for 0 to 1000 hertz will pick from W1 window, which basically this is low frequency band. So the spectrum will be picked from W1 window, and this is the high frequency. So the spectrum will be picked from smaller size window. This band edges I've defined here, and this the code for that. If a particular frequency is in between this, is in between the small frequency range, then then use the first window, which is the longer size window, and similarly for all the three, and I'll append I have appended all these spectrum in these three: P lock, location, P magnitude, and P phase. For all, it contains information from all the three windows. The sound is converted back into the time domain after getting all the frequency component. I have converted it back into the time domain to listen to the sound. So this is for converting it back into the time domain, and sound I've got it. It seems comparative to the CQ method. The signal that I have, second sound signal that I have used is this. So this sound, I'll play it once. This sounding more persuasive, and it has transient attacks. Basically, it has short energy bursts, which is ideal for temporal resolution evaluation. So for this one, CQT performed really bad, while while my algorithm did did quite better than CQT here. So basically, the algorithm that we use for analysis also depends on the type of sound that we are using. And so yeah, in conclusion, this algorithm was just inspired by CQT, but just implemented using just three window sizes and peak selection. It may not be optimal in every case, but it shows that even a simple approach improves over fixed window STFT or CQT in some cases.